Empty space is often described as nothing. Modern physics disagrees. Even in regions stripped of matter and radiation, experiments show that space does not remain inactive. Quantum fields fluctuate, energy densities shift, and geometry itself cannot be treated as a fixed backdrop. This is not speculation. It is a conclusion drawn from decades of measurements, from particle accelerators to cosmological observations. In this video, we explore what spacetime is actually made of when examined at its smallest meaningful scales. We will follow photons, not as symbols, but as physical entities that move according to geometry with extreme sensitivity. Their behavior places strict limits on how restless spacetime can be, and those limits already tell us which ideas survive contact with data. We'll take our time, beginning with physics that has stood up to decades of testing, before easing toward the edge of what we can currently explain. And in part 1, we turn to a quiet but unsettling thought: why empty space never truly stays at rest. Empty space is unstable by necessity, not by interpretation. This is the first constraint imposed by modern physics, and it emerges not from speculation but from repeated measurement. Whenever experiments attempt to remove matter, radiation, heat, and charge from a region, something measurable remains. Instruments detect activity that cannot be attributed to particles passing through, residual gas, or experimental noise. Space itself continues to participate. This refusal of space to settle appears only when physics abandons everyday scales. At human distances, emptiness seems convincing because interactions average out. Interstellar space, for example, contains fewer than 1 atom per cubic centimeter, according to measurements summarized by NASA and ESA. Even in regions between galaxies, density drops to fractions of an atom per cubic meter. By classical reasoning, this should approach nothing. Yet classical reasoning fails precisely where precision improves. Quantum field theory insists that fields exist everywhere, independent of whether particles are present. These fields are not optional constructs. They are required to account for outcomes measured at particle accelerators to more than 12 decimal places. The electron's magnetic moment, verified through experiments at CERN and SLAC, agrees with theoretical predictions only when vacuum fluctuations are included. Remove those fluctuations from the equations and the predictions collapse. The vacuum state in quantum theory is not empty. It is the lowest energy configuration of fields, not their absence. Even at this minimum, fluctuations persist because energy and time cannot be simultaneously specified with arbitrary precision. This constraint is not philosophical. It is enforced by experimental data collected since the early 20th century and confirmed across countless independent systems. One of the clearest demonstrations appeared in 1948, when Dutch physicist Hendrik Casimir calculated that 2 uncharged conducting plates, placed a few micrometers apart in a vacuum, should attract each other. The effect had no classical explanation. No electric charge, no magnetic interaction, no residual gas pressure could account for it. The force arises because the quantum electromagnetic field cannot sustain the same spectrum of modes between the plates as it can outside them. The allowed configurations are restricted by geometry. Fewer modes correspond to lower energy. The imbalance produces a force. When this effect was measured directly, decades later, using separations of roughly 1 micrometer and forces on the order of nanonewtons, the results matched Casimir's prediction. Space responded to boundaries. Geometry altered energy. Emptiness behaved differently, depending on structure. This behavior is not confined to laboratory scales. On the largest observable distances, the same vacuum fluctuations leave detectable traces. Observations of the cosmic microwave background by NASA's Wilkinson Microwave Anisotropy Probe and ESA's Planck satellite reveal temperature variations of roughly 1 part in 100,000. These variations are not instrumental artifacts. They are consistent across frequencies, detectors, and analysis methods. Those small differences correspond to density variations in the early universe, amplified over billions of years by gravitational attraction. According to standard cosmology, they originated as quantum fluctuations when the universe was less than a fraction of a second old. What began at subatomic scales later shaped galaxies, clusters, and the filamentary structure of the cosmos. Space carried memory of its earliest activity. Photons are central to this story because they interact directly with geometry and fields without the complications introduced by mass. A photon has no rest frame. Its behavior depends entirely on the structure it moves through. When light travels from a distant source to a detector, it integrates conditions along its entire path. That path may span billions of years and cross regions with varying gravitational potential, expansion rates, and field configurations. Observations from the James Webb Space Telescope illustrate this integration with remarkable clarity. JWST detects infrared photons emitted more than 13 billion years ago. These photons originated in young galaxies, traveled through expanding spacetime, passed near massive structures, and reached a detector cooled to a few Kelvin above absolute zero. Their spectra remain sharply defined. Their coherence persists. This persistence places strict limits on how irregular spacetime can be at large scales. If geometry fluctuated too strongly, phase coherence would be lost, spectral lines would smear. Arrival times would scatter beyond observed limits. They do not. The universe allows activity, but enforces discipline. The tension emerges when quantum field theory is combined with general relativity. Quantum fields fluctuate, and fluctuations carry energy. General relativity states that energy influences geometry. Taken together, these principles imply that spacetime itself cannot remain perfectly smooth at all scales. If energy fluctuates, geometry must respond. Physicist John Wheeler confronted this implication in the 1950s. He proposed that at sufficiently small distances, spacetime would exhibit extreme fluctuations, a regime he later described as quantum foam. His language was technical, not metaphorical. Classical notions of distance, duration, and localization cease to function once gravitational effects of quantum fluctuations become unavoidable. The scale at which this breakdown occurs is set by fundamental constants. Combining the gravitational constant, the speed of light, and Planck's constant yields the Planck length, approximately 1/6 meters. At this scale, attempting to localize an event requires energies so large that spacetime curvature becomes significant. Measurement interferes with what is being measured in an unavoidable way. This limit is not arbitrary. It arises independently in multiple theoretical frameworks. Both quantum mechanics and general relativity point toward it when pushed beyond their comfortable domains. Distance and duration lose operational meaning. Geometry resists being treated as a continuous background. Photons again become essential probes. Because they respond sensitively to geometry, even minute irregularities could influence their propagation. Some theoretical models predict effects such as energy-dependent delays, phase dispersion, or tiny deflections accumulating over cosmic distances. These effects would be subtle, far below everyday detection thresholds. But given enough distance, even small deviations could become measurable. This motivated careful analysis of astrophysical events that produce high-energy photons over short time intervals. Gamma-ray bursts serve this role. They release enormous energy in brief flashes, producing photons spanning wide energy ranges. NASA's Fermi Gamma-ray Space Telescope has monitored these events since 2008. Analyses of bursts originating billions of light-years away show that photons across different energies arrive within milliseconds of one another. Given travel times exceeding 10 billion years, this simultaneity is striking. Many simple models of spacetime fluctuations predict delays that are not observed. Those models are effectively ruled out. The lesson is precise. Spacetime may fluctuate at small scales, but any such fluctuations must preserve key symmetries at observable distances. Lorentz invariance, the principle that the laws of physics remain the same for all observers moving at constant velocity, survives every test so far. Experiments using particle accelerators, atomic clocks, and astrophysical observations consistently confirm this symmetry to extraordinary precision. The absence of observed violations does not imply a perfectly smooth underlying structure. It implies constraint. Activity exists, but it averages out in ways that preserve symmetry when viewed at larger scales. The vacuum is restless, yet ordered. Historical development reinforces this view. Classical physics treated space as a passive arena. Einstein replaced that notion by showing that geometry responds dynamically to energy and momentum. Quantum theory then demonstrated that fields cannot be fully at rest. Modern physics inherits both insights. Space participates, but within strict limits enforced by symmetry and consistency. Gravitational waves provide further confirmation. Detected directly by the LIGO observatories in 2015, these waves are oscillations of spacetime itself. They propagate at the speed of light and carry energy across vast distances. Their detection confirms that geometry is not static. It can move, deform, and transmit information. Yet even these waves preserve coherence over millions of light-years. The signals recorded from merging black holes match predictions derived from general relativity with remarkable accuracy. Geometry can oscillate violently and still obey precise rules. This combination of activity and restraint defines the modern picture. Space is not empty in the classical sense. It supports fields, stores constrained energy, and responds to geometry. Photons do not pass through nothing. They traverse an environment shaped by quantum and gravitational principles working together. What remains unresolved is how this structure behaves at the smallest scales, where quantum fluctuations of geometry become unavoidable. Existing theories identify limits, but stop short of a complete description. Some approaches suggest spacetime is built from discrete elements. Others propose that geometry emerges from deeper relations involving quantum information. None have been confirmed, but all must reproduce the observed discipline of photons and fields at accessible scales. The evidence assembled so far allows little flexibility. Space cannot be inert. It cannot be wildly unstable. It must carry structure that remains hidden, except through careful measurement. Every observation narrows the range of viable descriptions. With this picture in place, attention turns to a boundary that keeps appearing again and again, the scale where smooth spacetime stops behaving as expected. It is a boundary revealed not by speculation, but by carefully extending theories that have already proven reliable, until their predictions no longer align. Part 2. Why does smooth spacetime break down at the same scale for all theories? There is a scale where every reliable theory of physics quietly gives up its authority. It is not announced by paradox, and it is not discovered by philosophical doubt. It appears when equations that work everywhere else begin to contradict one another in precise, unavoidable ways. Smooth spacetime does not fail gradually. It fails sharply at the same boundary, no matter which path physics takes to reach it. At everyday distances, spacetime behaves exactly as expected. Lengths can be measured, durations can be compared, and events can be ordered without ambiguity. General relativity describes gravity as the curvature of spacetime, and does so with astonishing accuracy. Quantum mechanics governs atoms, radiation, and fields with predictions confirmed to more than 10 decimal places. For decades, these two frameworks appeared to occupy separate domains, one large and one small, without interference. That separation ends when scale is pushed far enough. As measurements shrink, quantum mechanics insists that uncertainty grows. Attempts to localize a particle more precisely demand higher energy. That energy cannot be ignored. According to general relativity, energy curves spacetime. When the energy required to probe a region becomes large enough, the geometry being measured begins to distort under the act of measurement itself. This is not a technical problem. It is a physical limit. The boundary where this happens is set by fundamental constants. When the speed of light, the gravitational constant, and Planck's constant are combined, they define a length of approximately 1.6 times 10 to the minus 35 meters. This distance is unimaginably small. It is far beyond the reach of any current or foreseeable experiment. Yet its significance does not come from accessibility. It comes from consistency. At this scale, the concepts of distance and duration lose their operational meaning. To probe smaller regions, the required energy would be sufficient to create strong gravitational effects, potentially forming microscopic black holes. Space can no longer be treated as a smooth arena where events simply occur. The geometry itself becomes involved. What is striking is that this boundary appears independently. General relativity reaches it when curvature becomes extreme. Quantum mechanics reaches it when uncertainty overwhelms localization. The two theories were developed for entirely different reasons, using different principles, yet they converge on the same scale. This convergence is not coincidence. It is constraint. Historical context reveals how unexpected this was. In the early 20th century, Einstein's theory of general relativity replaced the idea of gravity as a force with geometry. Space and time became dynamic, responding to mass and energy. This framework explained planetary motion, gravitational lensing, and the expansion of the universe, all later confirmed by observations from NASA missions and ground-based observatories. Quantum mechanics emerged separately, driven by the behavior of atoms and radiation. It introduced uncertainty as a fundamental feature, not a limitation of measurement. Experiments such as the double-slit interference of electrons and photons confirmed that nature does not permit exact trajectories at small scales. For decades, these theories coexisted without conflict because they were applied in different regimes. But when physicists attempted to describe situations where both strong gravity and quantum effects are unavoidable, such as near singularities or at the earliest moments of the universe, the smooth picture fractured. NASA's observations of black holes illustrate one side of this fracture. Data from the Event Horizon Telescope and X-ray measurements from the Chandra Observatory confirm that space-time curvature becomes extreme near a black hole's boundary. Classical geometry predicts singularities where curvature diverges. These predictions signal the breakdown of the theory, not its triumph. They indicate where additional physics must enter. On the other side, quantum field theory predicts fluctuations that grow without bound as scales shrink. Vacuum energy becomes increasingly difficult to define, and calculations diverge unless artificial cutoffs are imposed. These divergences are not mathematical accidents. They reflect the failure of assuming a smooth background down to arbitrarily small distances. The Planck scale marks the point where both failures occur simultaneously. Below it, neither classical geometry nor standard quantum descriptions remain self-consistent. Spacetime cannot remain smooth because smoothness itself requires that distances and durations be definable independent of energy. At this boundary, that independence vanishes. Observations of the early universe provide indirect support for this conclusion. Measurements of the cosmic microwave background by ESA's Planck satellite reveal fluctuations consistent with quantum origins, yet constrained by large-scale geometry. These patterns suggest that spacetime behaved differently at the universe's beginning, when densities and energies were far beyond current laboratory conditions. James Webb Space Telescope observations extend this story. By detecting galaxies formed less than 1 billion years after the Big Bang, JWST confirms that structure emerged rapidly. Such early organization implies that spacetime and quantum fields interacted under extreme conditions, governed by rules not fully captured by either existing framework alone. The persistence of smooth behavior at large scales is equally important. Despite the breakdown predicted at the Planck scale, spacetime appears continuous and well-behaved across astronomical distances. Gravitational waves detected by LIGO propagate with coherence across millions of light-years. Light from distant quasars maintains sharp spectral features after traveling for most of the universe's history. These facts impose strict conditions on any deeper description. The message is clear: whatever replaces smooth spacetime at the smallest scales must reproduce smoothness at larger ones. The breakdown is not chaos. It is controlled. Physicists have proposed multiple approaches to address this boundary. Some suggest that spacetime is composed of discrete elements, like a network woven from fundamental units. Others propose that geometry emerges from deeper relations involving quantum information. Each approach attempts to explain why smooth spacetime works where it does, and why it must fail where it cannot. What unites these efforts is recognition of the same limit. No credible theory allows spacetime to remain continuous and classical all the way down. The Planck scale is not an arbitrary invention. It is the point where known principles intersect and constrain one another. Carl Sagan once remarked, "Somewhere, something incredible is waiting to be known." In this context, that statement reflects not wonder, but discipline. The breakdown of smooth spacetime is not a mystery added to physics. It is a boundary drawn by the theories that have already earned our trust. The implications are precise. Distance cannot be subdivided indefinitely. Duration cannot be refined without consequence. Events cannot always be cleanly separated. These are not failures of measurement. They are features of nature revealed when physics is applied consistently. As this boundary becomes clearer, attention shifts to what lies beneath smooth geometry and how a deeper structure might shape the behavior of fields and particles, while still allowing the large-scale order we see across the universe. Part 3. Why does applying quantum mechanics to gravity turn space-time into foam? There is a moment when gravity stops behaving like a smooth curve and begins to act like something unstable, fragmented, and restless. That moment is not reached by imagination. It is reached by calculation. When the rules of quantum mechanics are applied not to particles inside spacetime, but to spacetime itself, geometry loses the ability to remain fixed. The result is not a minor correction. It is a complete change in character. In classical physics, spacetime is continuous. Between any 2 points, another point can always be inserted. Distances can be subdivided without limit. This assumption underlies both Newtonian physics and Einstein's general relativity. Even when spacetime curves strongly near massive objects, it remains smooth. Geometry bends, but it does not tear. Quantum mechanics does not permit this quiet continuity. At small scales, quantum theory imposes unavoidable uncertainty. When applied to particles, this uncertainty limits how precisely position and momentum can be known at the same time. This principle is not a statement about imperfect instruments. It is a structural feature of nature, confirmed in experiments ranging from electron diffraction to atomic spectroscopy. The behavior of matter simply does not allow sharp localization without consequence. When this uncertainty is transferred from particles to spacetime itself, the implications are severe. If geometry is subject to quantum uncertainty, then distances cannot remain well-defined at arbitrarily small scales. Curvature cannot remain fixed. The smooth fabric described by general relativity begins to fluctuate. John Wheeler recognized this in the 1950s while working on the problem of quantum gravity. He realized that if spacetime geometry is treated as a quantum object, then, at sufficiently small scales, it must fluctuate violently. He later referred to this regime as quantum foam. His description was technical, not metaphorical. Geometry itself becomes unstable, with rapid changes in curvature, topology, and causal structure. This instability is not optional. It follows directly from applying quantum uncertainty to gravitational fields. Gravity is unique among forces because it is geometry. The gravitational field does not live inside spacetime. It defines spacetime. When quantum mechanics is applied to electromagnetism, fluctuations occur in the electromagnetic field while spacetime remains fixed. When quantum mechanics is applied to gravity, the stage itself becomes uncertain. This distinction is crucial. In quantum field theory, vacuum fluctuations occur within spacetime. In quantum gravity, spacetime itself fluctuates. The difference is not semantic. It determines whether geometry remains a background or becomes a participant. The scale at which these effects become unavoidable is again set by fundamental constants. When the energy required to localize an event reaches a level where gravitational effects become strong, spacetime responds. Attempting to confine energy within an extremely small region causes curvature to increase. Beyond a certain point, further localization increases gravitational distortion. Faster than measurement, precision improves. At approximately 1.6 times 10 to the minus 35 meters, the Planck length, this feedback becomes dominant. Below this scale, classical geometry loses operational meaning. Spacetime can no longer be treated as a smooth manifold. It becomes dynamic in a new way. Wheeler's insight was not based on speculation about exotic objects. It followed from consistency. Quantum mechanics demands uncertainty. General relativity demands that energy influences geometry. Taken together, they demand fluctuating spacetime. Later developments reinforced this conclusion. In the 1960s and 70s, physicists studying perturbative quantum gravity found that calculations diverged uncontrollably at small scales. Unlike quantum electrodynamics, where infinities can be systematically removed through renormalization, gravity resisted such treatment. The divergences were not technical inconveniences. They signaled that smooth spacetime was being pushed beyond its domain of validity. Astrophysical observations do not contradict this picture. They constrain it. Light traveling across the universe remains remarkably coherent. Observations of distant quasars show sharp interference patterns and stable spectra. Gamma-ray bursts observed by NASA's Fermi telescope show no evidence of large energy-dependent delays. These facts rule out violent spacetime fluctuations at large scales. But quantum foam is not predicted to appear at large scales. It is confined to the smallest distances, far below direct observation. Its effects must average out when viewed from afar. This averaging is essential. Any viable description of quantum spacetime must reproduce classical geometry at scales accessible to measurement. The foam cannot leak into everyday physics unchecked. It must remain confined, hidden beneath layers of effective smoothness. Different approaches to quantum gravity attempt to describe this regime in different ways. Loop quantum gravity proposes that geometry is built from discrete units, with areas and volumes taking on quantized values. Causal dynamical triangulations model spacetime as emerging from the statistical behavior of simple building blocks assembled according to strict rules. String theory replaces point-like particles with extended objects, smoothing interactions at short distances and altering how spacetime behaves. Despite their differences, these approaches share a common motivation. Smooth spacetime cannot survive the application of quantum principles to gravity. Something more fundamental must replace it. Photons offer a subtle window into this structure. Because they respond directly to geometry, their propagation could, in principle, reveal cumulative effects of microscopic fluctuations. This possibility has driven careful analysis of astronomical data. So far, no definitive signal of spacetime foam has been detected. This absence is not failure. It is guidance. It tells us that whatever form quantum spacetime takes, it preserves coherence with extraordinary efficiency. Fluctuations must be tightly constrained. They cannot produce large violations of causality, locality, or symmetry at observable scales. Locality itself becomes approximate in this regime. At macroscopic scales, events are well ordered. Causes precede effects. Signals propagate within well-defined light cones. At Planck scale distances, this structure may blur. Not because causality disappears, but because the notion of a sharply defined event loses meaning. In Wheeler's picture, spacetime at the smallest scales resembles a constantly shifting structure where connections form and dissolve rapidly. The precise topology becomes unstable. Paths that appear distinct at larger scales may merge or fluctuate at smaller ones. This does not imply randomness without rule. The fluctuations are governed by quantum principles and constrained by consistency with large-scale observations. The foam is not chaos. It is structured uncertainty. Historical developments underline the seriousness of this conclusion. Every time physics has attempted to push a classical concept beyond its domain, the concept has fractured. Absolute simultaneity collapsed under relativity. Deterministic trajectories collapsed under quantum mechanics. Smooth spacetime collapse under quantum gravity. H-collapse did not destroy physics. It deepened it. Carl Sagan once noted, "Science is a way of thinking, much more than it is a body of knowledge." In this context, that way of thinking demands that spacetime be treated not as sacred, but as subject to the same scrutiny as any other physical concept. Observations from NASA and ESA missions support this disciplined view. Gravitational waves propagate cleanly across cosmic distances. Light retains coherence. Large-scale geometry behaves classically. These facts anchor theory. Any deeper description must respect them. Quantum foam is not an optional embellishment. It is the minimal consequence of applying quantum mechanics to gravity honestly. Whether it takes the form Wheeler imagined, or a more refined structure, remains unknown. What is known is that smooth spacetime cannot be fundamental. Geometry becomes active, locality becomes approximate. The universe's structure is no longer something photons merely traverse. It becomes something they continuously respond to, even if that response is subtle and well hidden. With this realization in mind, a new difficulty comes into view. Even if spacetime is restless at its foundation, quantum fields continue to propagate without falling apart, forcing a clear distinction between changes in spacetime geometry and the fluctuations inherent to the fields it supports. Part 4. Why aren't quantum vacuum fluctuations the same as spacetime foam? One of the most damaging mistakes in modern physics begins quietly, with a single substitution that feels harmless. It happens when the restless behavior of quantum fields is taken as evidence that spacetime itself must behave the same way. At first glance, the distinction seems subtle. In practice, it separates two entirely different layers of reality. Crossing that boundary without care leads to incorrect conclusions about energy, causality, and even what it means for events to be connected at all. Quantum vacuum fluctuations arise from quantum field theory. They occur because fields exist everywhere and cannot be completely motionless. Even in their lowest energy state, fields retain residual activity enforced by uncertainty. These fluctuations are real, measurable, and experimentally confirmed. They influence particle properties, atomic transitions, and forces between objects. Yet they all share one crucial assumption. They occur on top of spacetime. The geometry itself remains fixed. Spacetime foam belongs to a different category entirely. It arises only when gravity is treated as a quantum phenomenon. In this case, spacetime is no longer a stage on which fluctuations occur. It becomes the object that fluctuates. Confusing these two regimes does not merely blur terminology. It collapses a structural distinction that physics depends on to remain internally consistent. The difference becomes clear when history is followed carefully. Quantum field theory was constructed in the middle of the 20th century to reconcile special relativity with quantum mechanics. Its success is unmatched. Predictions derived from quantum electrodynamics agree with experiments to better than 1 part in a trillion. The theory assumes a background spacetime with well-defined distances and durations. Fields exist everywhere in that background, and particles emerge as excitations of those fields. Vacuum fluctuations are an unavoidable feature of this framework. They arise because the lowest energy configuration of a field is not equivalent to zero activity. Energy and time cannot both be specified with arbitrary precision, and this constraint forces residual motion. The effect is not abstract. It is measured. The Casimir effect provides one of the clearest demonstrations. Two uncharged metal plates placed a few micrometers apart in a vacuum attract one another. The force does not arise from hidden charges or residual gas. It arises because the electromagnetic field cannot support the same spectrum of fluctuations between the plates as it can outside them. Geometry restricts field behavior. Energy changes. A force appears. This phenomenon has been measured repeatedly since the late 1990s with increasing precision. It confirms that vacuum fluctuations are sensitive to boundary conditions. But spacetime itself does not fluctuate in these experiments. The plates exist in a fixed geometric background. The field responds. Geometry does not. This distinction holds across all of quantum field theory. Virtual particles, vacuum polarization, and zero-point energy are all descriptions of field behavior within spacetime. None of them require spacetime itself to lose its smoothness. None of them involve uncertainty in distance or duration. Spacetime foam enters only when gravity is treated quantum mechanically. Gravity differs from other forces because it is geometry. The gravitational field does not exist within spacetime. It defines spacetime. When gravity is quantized, uncertainty applies to geometry itself. Distances, areas, and volumes become subject to quantum fluctuations. This is not a reinterpretation of field behavior. It is a change in what is fluctuating. John Wheeler understood this difference with unusual clarity. In the 1950s, while studying the consequences of combining quantum mechanics with general relativity, he realized that applying uncertainty to spacetime geometry would destabilize classical notions of continuity. At sufficiently small scales, geometry would fluctuate violently. He referred to this regime as quantum foam. Wheeler was careful not to confuse this with vacuum fluctuations. The foam was not activity within spacetime. It was activity of spacetime. This distinction matters because quantum vacuum fluctuations can exist without gravity. They are present in flat spacetime, governed by special relativity. Spacetime foam cannot. It emerges only when gravity is included and treated consistently with quantum principles. Observational data reinforce this separation. NASA and ESA missions have placed strong limits on how spacetime behaves at observable scales. Light from distant quasars shows sharp interference patterns. Gamma-ray bursts observed by the Fermi telescope display no large energy-dependent delays. Gravitational waves detected by LIGO propagate coherently across millions of light-years. These observations confirm that spacetime behaves smoothly at large distances. Quantum vacuum fluctuations do not threaten this smoothness. They average out. Their effects are local and constrained. Spacetime foam, by contrast, would threaten coherence if it extended unchecked into observable regimes. That it does not tells us something essential. If spacetime foam exists, it must be confined to scales far smaller than anything currently accessible. The confusion between vacuum fluctuations and spacetime foam often leads to exaggerated claims. Vacuum energy is sometimes treated as evidence that spacetime itself is unstable. But vacuum energy is defined within a fixed geometry. It does not imply that geometry fluctuates. It implies that fields respond to boundary conditions and constraints imposed by geometry. This confusion becomes particularly problematic in discussions of dark energy. The observed acceleration of cosmic expansion, measured by supernova surveys and confirmed by ESA's Planck mission, is often compared to vacuum energy density. Yet the theoretical vacuum energy predicted by quantum field theory exceeds observed values by many orders of magnitude. This discrepancy is not evidence that spacetime foam dominates cosmology. It is evidence that vacuum energy calculations depend sensitively on assumptions about geometry and cutoffs. Spacetime foam does not resolve this discrepancy. It deepens it. It asks how geometry itself behaves when quantum principles apply. It does not equate field fluctuations with geometric instability. Another area where confusion arises is entanglement. Quantum fields can exhibit entanglement across space-like separations. This does not require spacetime itself to fluctuate. Entanglement occurs within a fixed causal structure. Spacetime foam, by contrast, may blur locality at the smallest scales, altering how events are connected. These are fundamentally different effects. Keeping this boundary clear prevents category errors. Fields fluctuate within spacetime. Geometry fluctuates only when gravity becomes quantum. Mixing the two leads to incorrect statements about causality, signal propagation, and information flow. Theoretical approaches to quantum gravity preserve this distinction even as they attempt to replace classical geometry. Loop quantum gravity quantizes geometric quantities directly. Areas and volumes take on discrete values. The fluctuations occur in geometry itself, not in fields living atop it. Causal dynamical triangulations model spacetime as emerging from the collective behavior of simple building blocks. Again, geometry is the object of quantization. String theory takes a different route, but the distinction remains. Quantum fields exist on extended objects, whose dynamics modify spacetime behavior at short distances. The background may become dynamic, but the difference between field activity and geometric fluctuation is preserved. None of these approaches treat vacuum fluctuations as equivalent to spacetime foam. They cannot. Doing so would collapse the logical structure of the theories. Observational constraints support this disciplined separation. Photons remain coherent across cosmic distances. Atomic clocks maintain synchronization. Interferometers detect gravitational waves with precise phase relationships. These facts would be impossible if spacetime itself fluctuated strongly at accessible scales. The foam, if real, must be hidden. It must influence physics indirectly, through subtle effects that average out. It must preserve symmetry and causality where they are observed. These requirements sharply restrict theoretical possibilities. This is why spacetime foam is not a metaphor. It is not a way of saying that space is busy or energetic. It is a precise statement about what happens when quantum uncertainty is applied to geometry rather than to fields. It represents a deeper layer of description, one that does not replace quantum field theory but underlies it. The distinction also explains why spacetime foam has not been directly observed. Vacuum fluctuations are accessible because they operate within spacetime. Spacetime foam operates beneath the framework that defines measurement itself. Its effects are suppressed, averaged, and constrained by the very structure it destabilizes. Carl Sagan once wrote, "Extraordinary claims require extraordinary evidence." In this context, the extraordinary claim would be that spacetime itself fluctuates. The evidence required is correspondingly strict. So far, nature has permitted no shortcuts. Only theories that respect the boundary between fields and geometry survive contact with data. The focus now narrows to something deceptively simple: light. Geometry guides every photon's path, and if that geometry is unstable at its foundation, then the continued precision of light points to an important clue that photons may preserve faint information about spacetime's smallest scale behavior, even after crossing the universe. Part 5. Why are photons the most sensitive witnesses of spacetime's smallest structure? A single photon can cross the entire observable universe without ever slowing down, without ever resting, and without ever separating itself from the geometry it travels through. That fact alone makes light unlike any other physical object we know, and it is precisely why photons become the most sensitive witnesses of spacetime's deepest structure. Photons carry no rest mass. This is not a descriptive label, but a physical constraint confirmed by every experiment that has ever measured the behavior of light. Because they have no rest mass, photons do not possess a rest frame. There is no valid physical perspective in which a photon is stationary. Its existence is inseparable from motion. It does not move through spacetime in the way matter does. It is guided by spacetime. In Einstein's theory of general relativity, massive objects follow paths that depend on both their motion and the curvature of spacetime. Photons are different. They follow the geometry itself with uncompromising precision. Their trajectories are null paths, determined entirely by spacetime structure, not by inertia. Any curvature, however small, leaves its imprint on the path of light. This sensitivity has been confirmed repeatedly through observation. Gravitational lensing, predicted by Einstein in 1915 and first observed during the solar eclipse of 1919, shows that light bends when spacetime is curved by mass. NASA and ESA have since observed this effect on enormous scales. Light from distant galaxies is distorted into arcs and rings by massive clusters, allowing astronomers to map invisible distributions of dark matter. Matter responds to gravity. Light traces geometry. Because photons lack mass, they do not resist changes in spacetime structure. A massive particle can, to some degree, average over small-scale irregularities due to inertia. Photons cannot. Any deviation in geometry, however subtle, alters their path. This is why light becomes a natural probe of spacetime at scales where matter becomes insensitive. This role becomes even more pronounced when photons travel vast distances. A photon emitted by a galaxy observed by the James Webb Space Telescope may have traveled for more than 13 billion years. During that time, it crossed expanding spacetime, regions of varying curvature, and environments permeated by quantum fields. It experienced every large-scale feature of the universe's geometry. If spacetime possessed small-scale irregularities that failed to average out, their cumulative effect would appear in the properties of that light. This possibility has driven careful experimental scrutiny. Astronomers analyze the coherence of light arriving from distant sources with extreme precision. Spectral lines emitted by atoms in remote galaxies remain sharp. Interference patterns persist. Arrival times of photons across wide energy ranges remain tightly correlated. These observations place strict limits on how spacetime can fluctuate over large distances. Gamma-ray bursts provide a particularly powerful test. These events release enormous energy in brief intervals, producing photons across a wide spectrum. NASA's Fermi Gamma-ray Space Telescope has monitored such bursts originating billions of light-years away. If spacetime fluctuations accumulated significantly, photons of different energies would arrive at measurably different times. They do not. Differences remain smaller than milliseconds after journeys lasting billions of years. This result does not eliminate the possibility of spacetime foam, it constrains it. Any microscopic irregularities must average out with extraordinary efficiency. The universe allows structure, but it enforces coherence. The story becomes deeper when quantum considerations are included. Photons are quantum objects. They exhibit wave-like behavior, interference, and entanglement. Their phase coherence can be tracked with extraordinary precision. In laboratory experiments, single photons can interfere with themselves, producing stable patterns that depend sensitively on path length differences smaller than the diameter of an atom. If spacetime geometry fluctuated strongly at small scales, maintaining this coherence over cosmic distances would be impossible. That it is maintained suggests that spacetime's smaller structure, if irregular, must be constrained in specific ways. The geometry cannot introduce random phase noise without violating observation. This has led physicists to view photons as probes not only of astrophysical sources, but of spacetime itself. Light carries information about the medium it traverses, even when that medium is spacetime. The absence of certain effects becomes as informative as their presence. Historical development highlights why this role of photons was not immediately obvious. Early quantum theory treated light primarily as a carrier of energy. Einstein's explanation of the photoelectric effect focused on energy quantization, not geometry. It was only after general relativity that the full significance of light's sensitivity to spacetime became clear. Later, quantum electrodynamics refined the description further. Vacuum polarization, photon scattering, and loop corrections showed that even in empty space, photons interact indirectly through fields. Yet all of this occurs within a fixed geometric background. When geometry itself becomes subject to quantum uncertainty, photons stand at the boundary between known physics and speculation. NASA's Cosmic Background Explorer, followed by WMAP, and ESA's Planck satellite, revealed another dimension of this sensitivity. The cosmic microwave background consists of photons that last scattered when the universe was about 380,000 years old. These photons preserve information about early spacetime geometry. Tiny temperature variations encode density fluctuations and curvature conditions present at that epoch. The fact that these patterns remain coherent across the sky confirms that spacetime behaved in a disciplined manner even under extreme early conditions. Whatever irregularities existed did not erase large-scale correlations. Geometry fluctuated, but within bounds. James Webb's Space Telescope observations now extend this record even closer to the beginning. By detecting galaxies formed within the first billion years, JWST captures photons that experienced early spacetime under intense conditions. Their properties further restrict how geometry could have behaved at small scales. Theoretical models, attempting to describe spacetime foam, must satisfy all of these constraints. They must allow microscopic fluctuations without producing macroscopic incoherence. They must preserve Lorentz symmetry at observable scales. They must allow photons to remain precise witnesses. Some models propose that spacetime has a discrete structure, composed of fundamental units. Others suggest that geometry emerges from deeper quantum relations. In each case, photons serve as tests. Any model that predicts measurable distortions inconsistent with observation is ruled out. This is why photons occupy a unique position. They are not merely messengers from distant objects. They are diagnostic tools for spacetime itself. They respond to geometry directly, without the buffering effects that protect massive particles from small-scale structure. Yet photons are also remarkably forgiving. Their sensitivity does not amplify noise indiscriminately. Instead, it integrates structure coherently. This dual role makes them reliable probes, rather than fragile indicators. The phrase often attributed to Carl Sagan, "The universe is under no obligation to make sense to you," applies here in a precise way. Photons do not simplify spacetime for us. They record it faithfully. It is our task to interpret what they carry. What remains unresolved is subtle. If spacetime fluctuates at the smallest scales, how do those fluctuations interact with quantum coherence? How do correlations survive? How does geometry remain both active and disciplined? Photons continue to provide clues. Each observation narrows possibilities. Each constraint removes entire classes of models. The absence of distortion becomes evidence of structure. Here, expectations meet an unexpected restraint. Photons interact directly with geometry, and spacetime foam should imprint itself along their paths. But the lack of clear signals points toward a deeper constraint on how spacetime behaves at its foundation. Part 6. Why would quantum foam leave traces on light crossing the universe? If spacetime truly fluctuates at its smallest scales, then light cannot cross the universe without consequence. This is not a dramatic claim, and it is not a speculative one. It is a direct implication of how photons interact with geometry. Light follows spacetime with absolute fidelity. If spacetime carries microscopic irregularities, even tightly constrained ones, then photons should carry a record of that journey, written not as obvious distortions, but as the faintest possible traces. At ordinary distances, these traces would be undetectable. A photon traveling a few meters, or even a few kilometers, would encounter fluctuations too small and too brief to leave any measurable imprint. But the universe offers distances far beyond any laboratory. When light travels for billions of years, even effects that are individually negligible can, in principle, accumulate. This idea has motivated decades of careful theoretical and observational work. In models where spacetime possesses a foamy structure near the Planck scale, geometry does not remain perfectly smooth along a photon's path. Instead, the effective distance a photon travels may fluctuate slightly around an average value. These fluctuations are not random in the everyday sense. They are constrained by symmetry, causality, and consistency with known physics. But they introduce the possibility that light accumulates tiny phase shifts as it propagates. Phase is not an abstract mathematical construct. It is a physical property that determines whether waves interfere constructively or destructively. In laboratory experiments, shifts in phase smaller than a fraction of a wavelength can be detected through interference. Astronomical observations extend this sensitivity across unimaginable distances. If spacetime foam introduced uncorrelated phase noise, interference patterns from distant sources would blur, spectral lines would lose sharpness, images of distant objects would degrade beyond what is observed. Yet they do not. This absence of obvious distortion is one of the strongest constraints on quantum gravity models. Still, absence does not mean irrelevance. Theoretical analyses distinguish between different kinds of cumulative effects. Some models predict phase noise that grows linearly with distance. Others predict growth proportional to the square root of distance, similar to a random walk. Still, others predict effects that saturate and stop growing beyond a certain scale. Observations rule out the strongest versions, but leave room for subtler ones. NASA's Hubble Space Telescope has played a central role in testing these ideas. By observing diffraction-limited images of distant quasars and active galactic nuclei, astronomers can assess whether spacetime fluctuations smear images beyond expected instrumental limits. Studies published in the early 2000s showed that Hubble images remain sharper than many foam models would allow. Those models were eliminated. The story deepened with gamma-ray observations. Gamma-ray bursts emit photons across a wide range of energies over very short timescales. If spacetime foam caused energy-dependent variations in photon speed, higher energy photons would arrive measurably earlier or later than lower energy ones after traveling billions of light years. NASA's Fermi Gamma-ray Space Telescope has tested this directly. The results are striking. Photons spanning orders of magnitude in energy arrive within milliseconds of each other, even after journeys exceeding 10 billion years. This observation rules out many scenarios in which spacetime foam produces strong dispersion. It does not rule out all possible effects, but it confines them to an extraordinarily narrow range. These constraints illustrate a critical principle. Any quantum structure of spacetime must be subtle enough to preserve the coherence of light over cosmic distances. Spacetime cannot behave like a turbulent medium that randomly scatters photons. It must behave like a system with deep internal order, even if that order differs from classical smoothness. Phase noise is not the only possible trace. Minute angular deflections provide another channel. If spacetime geometry fluctuates, the direction of photon propagation could undergo tiny deviations. Over long distances, these could accumulate into measurable blurring of point sources. Again, observation provide guidance. Very long baseline interferometry combines radio telescopes across Earth to achieve angular resolution, capable of detecting distortions far smaller than any single instrument could measure. Images of distant quasars remain sharply defined. Any space-time-induced angular wandering must therefore be extremely limited. Energy-dependent delays, phase coherence, angular stability all converge on the same conclusion. If space-time foam exists, its effects on light must be delicately balanced. They must be present enough to matter at fundamental scales, but suppressed enough to evade detection across the observable universe. This balance is not arbitrary. It reflects the survival of Lorentz symmetry at accessible energies. Special relativity has been tested to extraordinary precision. Any model of space-time foam must reproduce this symmetry effectively, even if it is broken or modified at the deepest levels. Theoretical physicists have explored mechanisms by which this could occur. Some propose that space-time fluctuations are strongly correlated, cancelling their effects over long distances. Others suggest that only transverse fluctuations occur, leaving photon phase largely intact. Still, others propose that quantum geometry interacts with light in ways that preserve average propagation speed exactly. Observations of the cosmic microwave background offer additional constraints. These photons have traveled since the universe was about 380,000 years old. Their temperature fluctuations encode early density variations with extraordinary precision. If space-time foam introduced uncontrolled noise, these patterns would be erased. They are not. ESA's Planck mission mapped the cosmic microwave background with resolution and sensitivity sufficient to detect deviations at the level of tens of microkelvin. The resulting power spectrum matches predictions of standard cosmology with remarkable accuracy. This coherence places limits on any cumulative spacetime effects acting on photons over the entire age of the universe. James Webb Space Telescope now extends this reach. By observing early galaxies and reionization-era structures, JWST captures light that traversed spacetime under conditions far more extreme than those present today. Its observations show no unexpected loss of coherence or unexplained dispersion. Whatever spacetime foam may be, it respects the same constraints. The cumulative picture is precise. Light is sensitive enough to detect even the faintest geometric irregularities. Yet, the universe preserves coherence across scales that dwarf any laboratory experiment. This combination is not paradoxical. It is informative. It suggests that spacetime foam, if real, is not a chaotic froth. It is structured. Its fluctuations are bounded, correlated, and disciplined. They may alter propagation at the smallest scales, but they do so in ways that average out with extraordinary efficiency. Theoretical models that survive observational scrutiny tend to share these features. They replace smooth geometry with discrete or relational structures that reproduce classical behavior when coarse-grained. In such models, photons interact with effective geometry rather than individual microscopic elements. The deeper structure remains hidden unless probed at energies far beyond current reach. Historical parallels help place this in context. At the beginning of the 20th century, atoms were proposed to explain discrete spectral lines long before individual atoms could be imaged. Their effects were inferred indirectly through careful measurement. In the same way, spacetime foam may leave indirect signatures in light without revealing itself directly. Carl Sagan once observed, "Somewhere, something incredible is waiting to be known." In this case, the waiting is enforced by nature itself. The traces, if they exist, are faint by design. They test not only instruments, but theoretical restraint. The absence of dramatic effects is not disappointing. It is a powerful result. It tells us that the universe is coherent at scales where coherence matters. It tells us that any deeper structure must honor the stability we observe. Light continues to cross the universe, carrying information about distant objects and about the medium it traverses. Each photon is both messenger and probe. Each observation tightens constraints, eliminating possibilities and sharpening understanding. Precision measurements have begun to speak through what they do not show. As photons arrive from quasars, billions of light-years away without the predicted signatures of quantum foam, many theoretical possibilities quietly fall away, revealing strong constraints on spacetime's underlying structure. Part 7. Why did distant quasars quietly rule out many quantum foam models? Some of the most decisive experiments in physics were never built by human hands. They were carried out by the universe itself, using distances no laboratory could ever reproduce. Long before physicists refined detectors or debated models of quantum spacetime, light had already begun its journey across billions of years, carrying with it a silent record of what spacetime allowed and what it did not. Quasars are among the most extreme light sources known. Powered by supermassive black holes, accreting matter at the centers of young galaxies, they emit enormous amounts of radiation across the electromagnetic spectrum. Many quasars observed today are more than 10 billion light-years away. The photons we receive from them began their journey when the universe was a small fraction of its current age. From the perspective of quantum gravity, this makes quasars invaluable. Their light has crossed most of the observable universe, traversing expanding spacetime, gravitational wells, intergalactic plasma, and whatever microscopic structure spacetime may possess. If quantum foam produced cumulative distortions in photon propagation, quasars would reveal it. The expectation was straightforward. Many early models of quantum foam predicted that spacetime fluctuations would introduce small, random phase shifts or angular deviations in light. Individually, these effects would be negligible. Over billions of light-years, however, they should accumulate. The result would be blurred images, smeared interference patterns, or energy-dependent distortions beyond what classical physics predicts. Astronomers knew exactly where to look. High-resolution imaging from the Hubble Space Telescope allowed researchers to examine distant quasars with extraordinary angular precision. These objects, effectively point sources at cosmological distances, provide clean tests. Any space-time-induced angular wandering would broaden their images beyond instrumental limits. In the early 2000s, detailed analyses compared observed quasar images with predictions from various quantum foam models. The result was unexpectedly clear. The images were too sharp. Interference fringes remained intact. Angular coherence persisted far beyond what many models allowed. Entire classes of foam models failed immediately. This was not a dramatic refutation. There were no headlines declaring a revolution. The data simply refused to cooperate with the theory. Models predicting linear accumulation of spacetime fluctuations with distance were incompatible with observation. Random walk models, where fluctuations grow with the square root of distance, were also tightly constrained. The universe had already performed the experiment, and the result was negative. Gamma-ray bursts added another layer of evidence. These brief, intense flashes of gamma radiation originate from massive stellar collapses or neutron-star mergers at cosmological distances. They release photons spanning wide energy ranges over milliseconds. This combination makes them powerful probes of energy-dependent propagation effects. If spacetime foam altered photon speeds differently depending on energy, higher energy photons would arrive earlier or later than lower energy ones after traveling billions of years. NASA's Fermi Gamma-Ray Space Telescope was designed to detect such effects with extreme sensitivity. The observations were precise. Across multiple gamma-ray bursts, photons spanning several orders of magnitude in energy arrived nearly simultaneously. Any energy-dependent delays were constrained to be far smaller than many quantum foam models predicted. Again, theory gave way quietly. No dramatic anomaly appeared. Instead, boundaries tightened. Models that predicted strong dispersion were eliminated. Others were forced into narrow parameter ranges. The absence of distortion became data. This pattern repeated across observational platforms. Very long baseline interferometry, which links radio telescopes across continents, achieved angular resolutions capable of detecting deviations far below what single instruments could resolve. Distant radio quasars remained stable. Phase coherence persisted. Spacetime, whatever its microscopic structure, preserved macroscopic order with remarkable fidelity. The cosmic microwave background provided yet another constraint. These photons have traveled since the universe was approximately 380,000 years old. They encode early density variations and curvature conditions with extraordinary precision. ESA's Planck mission mapped these fluctuations across the entire sky, producing a power spectrum consistent with standard cosmology to high accuracy. If space-time foam introduced uncontrolled phase noise or angular distortions, these delicate patterns would be erased. They were not. The universe preserved correlations across scales spanning the entire sky. This convergence of evidence tells a clear story. Many simple models of quantum foam are not compatible with reality. They predict effects that nature does not produce. What remains are models in which space-time fluctuations are tightly constrained, highly correlated, or suppressed in ways that preserve large-scale coherence. The foam, if it exists, cannot behave like random turbulence. It must obey rules as strict as those governing classical spacetime, even if those rules emerge from deeper structure. The elimination of models through observation is a familiar process in physics. The Michelson-Morley experiment quietly ruled out the luminiferous ether. The perihelion precession of Mercury constrained modifications to Newtonian gravity. In each case, data did not shout. It simply persisted. Quasars played a similar role for quantum spacetime. The story carries an important lesson. Theories of quantum gravity cannot be evaluated solely by mathematical elegance or internal consistency. They must survive contact with the universe as it is observed. Even when direct experiments at the Planck scale are impossible, indirect constraints can be devastatingly effective. Carl Sagan once noted, "If you wish to make an apple pie from scratch, you must first invent the universe." In this context, the universe has already done the baking. The ingredients are fixed. The outcome is visible. Any theoretical recipe that produces a different result must be discarded. This quiet elimination reshaped the field. Researchers began focusing on models that preserve Lorentz symmetry at observable scales, that average microscopic fluctuations efficiently, and that reproduce classical geometry with extraordinary accuracy. Quantum foam, once imagined as wildly turbulent, became increasingly constrained. The absence of distortion does not imply the absence of structure. It implies discipline. Space-time may fluctuate, but it does so in a way that respects coherence, causality, and symmetry. The universe tolerates no excess noise. Photons arrive on time. Images remain sharp. Interférences survivent. These facts narrow the path forward. They tell us that any successful theory of quantum spacetime must explain not only how geometry fluctuates, but how those fluctuations remain hidden across cosmic distances. What remains now is a narrower landscape. After light from across the universe has already excluded so many possibilities, only a few forms of quantum spacetime persist, constrained tightly enough to preserve the behavior of light itself. Part 8. Why doesn't a fluctuating spacetime destroy the speed of light? If spacetime truly fluctuates at its smallest scales, then the constancy of the speed of light should have been the first casualty. That is the uncomfortable expectation many physicists faced when quantum gravity entered serious discussion. Yet observation says otherwise. Across laboratories, across galaxies, across billions of years, light arrives with the same invariant speed, not approximately, not on average, precisely. This persistence is not a coincidence, and it is not a loophole. It is a constraint that any description of quantum spacetime must obey. The speed of light occupies a unique position in physics. In Einstein's theory of special relativity, it is not merely the speed at which photons travel. It is the conversion factor between space and time. It defines causal structure. It determines which events can influence which others. It sets the boundary between what can be connected and what must remain separate. This principle has been tested relentlessly. Atomic clocks flown on aircraft and satellites tick at rates predicted by relativity. Particle accelerators operate only because relativistic timing holds exactly. Signals exchanged between spacecraft and Earth arrive precisely when expected. NASA's Deep Space Network relies on this constancy to navigate probes across the solar system with kilometer accuracy over distances measured in billions of kilometers. If space-time fluctuations altered the speed of light even slightly at observable scales, these systems would fail. They do not. The challenge emerges when quantum gravity enters the picture. If space-time geometry fluctuates, if distances and durations are not perfectly defined at the smallest scales, then one might expect photons to experience variable effective paths. Some early models of quantum foam took this intuition literally. They predicted that light would scatter, slow, or speed up depending on microscopic geometry. In these models, the speed of light became an emergent, approximate quantity. Nature rejected them. Gamma-ray burst observations provide one of the clearest demonstrations. These bursts emit photons across a wide energy range in extremely short intervals. If space-time fluctuations altered photon speed in an energy-dependent way, higher energy photons would arrive earlier or later than lower energy ones after traveling billions of years. NASA's Fermi Gamma-ray Space Telescope has tested this directly. The result is consistent across many events. Photons arrive together within tight limits. Any deviation from constant speed is constrained to levels far smaller than many theoretical models predicted. The universe preserves the speed of light with extraordinary discipline. The same conclusion emerges from observations of distant quasars. Light from these objects travels across most of the observable universe. Its spectral lines remain sharp. Interference patterns remain intact. If space-time fluctuations accumulated unchecked, these signatures would degrade. They do not. This forces a revision of intuition. Space-time can fluctuate without destroying relativistic symmetry. The key lies in how those fluctuations are organized. Random, uncorrelated irregularities would indeed scramble photon propagation. But quantum gravity does not permit arbitrary randomness. Any viable theory must reproduce Lorentz symmetry at scales accessible to measurement. Lorentz symmetry is not an optional aesthetic choice. It is one of the most precisely tested principles in physics. Experiments using particle accelerators, atomic clocks, and astrophysical observations constrain violations to parts per billion or better. The absence of observed violations is itself data. This does not imply that space-time is smooth at all scales. It implies that fluctuations, if present, are constrained in such a way that symmetry emerges when averaged over larger distances. Smoothness may be effective rather than fundamental. Historical context clarifies why this distinction matters. In the 19th century, physicists assumed that light traveled through a medium called the ether. Experiments eventually showed that no such preferred frame exists. The Michelson-Morley experiment did not detect motion through an ether. Instead of abandoning light, physics abandoned the ether. Einstein elevated this result into a principle. Quantum gravity faces a similar moment. If space-time foam introduced preferred directions, frames, or speeds at observable scales, those would have been detected. They were not. Theories must adapt. Some modern approaches incorporate this lesson directly. In loop quantum gravity, geometric quantities are quantized, but the theory is constructed to recover Lorentz symmetry at large scales. In causal dynamical triangulations, space-time emerges from discrete building blocks whose collective behavior reproduces relativistic symmetry. In string theory, extended objects smooth interactions at short distances while preserving symmetry at low energies. Different mechanisms, same requirement. The absence of violations does not imply the absence of structure. It implies coherence. An instructive analogy comes from condensed matter physics. A crystal lattice breaks continuous symmetry at the microscopic level, yet waves propagating through the lattice can obey effective equations that appear perfectly symmetric at long wavelengths. The underlying discreteness does not announce itself unless probed at sufficiently high resolution. Spacetime may behave similarly. Microscopic structure could exist without spoiling macroscopic symmetry. The speed of light remains invariant because it is an emergent property enforced by deeper constraints. Gravitational wave observations reinforce this view. The waves detected by LIGO propagate at the speed of light to within extremely tight bounds. They originate from violent events, such as black hole mergers, where spacetime curvature is extreme. Yet even under these conditions, propagation respects relativistic timing. ESA and NASA observations of neutron star mergers further confirmed this. In 2017, Gravitational waves and electromagnetic signals from the same event arrived within seconds of each other after traveling more than 100 million light-years. This simultaneity constrains any deviation between gravitational and electromagnetic propagation speeds to extraordinary precision. If spacetime fluctuations disrupted light speed, such agreement would be impossible. The conclusion is firm. The universe enforces relativistic symmetry with rigor. Any quantum description of spacetime must respect this enforcement. This realization reshaped how physicists think about quantum foam. Early images of violent turbulence gave way to subtler pictures. Fluctuations may exist, but they are correlated. They may modify geometry, but they do so without introducing preferred frames. They may blur locality at the smallest scales, but they preserve causality at larger ones. The speed of light survives not because spacetime is smooth, but because spacetime is constrained. Carl Sagan once said, "Nature is always more subtle than we suppose." In this case, subtlety is a requirement. The universe allows complexity beneath simplicity, but it does not tolerate inconsistency. Photons continue to travel at the same speed because that speed is woven into the structure of causality itself. Alter it, and the universe would no longer behave as observed. The absence of violation is not disappointing. It is revealing. It tells us that quantum spacetime, whatever its true form, must reproduce the symmetries that have survived every experimental test. It tells us that the frontier lies not in breaking relativity, but in understanding how it emerges from deeper structure. Once the speed of light is preserved despite underlying fluctuations, many possibilities quietly disappear. What remains are geometries constrained tightly enough to respect symmetry, pointing toward a spacetime that may be structured in discrete elements rather than a smooth continuum. Part 9. Why might spacetime be built from discrete structures rather than continuity? At a certain point, smooth spacetime stops cooperating with physics. It does not do so noisily or catastrophically. It simply refuses to remain mathematically consistent when pushed beyond a specific scale. That refusal is the reason this question exists at all. If spacetime cannot remain continuous under the combined demands of quantum mechanics and gravity, then continuity itself may not be fundamental. For more than a century, physics treated spacetime as a continuum. In Einstein's general relativity, spacetime is smooth by construction. Curvature varies from place to place, but between any 2 points, there are infinitely many others. Distances and durations can be subdivided without limit. This assumption worked extraordinarily well. It predicted gravitational lensing, time dilation, black holes, and gravitational waves, all later confirmed by observations from NASA, ESA, and ground-based observatories. Quantum mechanics, however, introduced a different lesson. Energy comes in discrete amounts. Atomic transitions occur in steps. Angular momentum is quantized. These were not philosophical choices. They were forced by experimental results. When physicists attempted to apply the same quantization principles to gravity, continuity became a liability. The problem appears when measurements approach the Planck scale, roughly 1.6 times 10 to the minus 35 meters. At this scale, attempts to localize events require energies so large that spacetime curvature can no longer be ignored. Classical geometry assumes that spacetime exists independently of what occupies it. Quantum gravity denies that separation. Measurement disturbs geometry itself. If geometry is subject to quantum uncertainty, then treating it as infinitely divisible becomes questionable. A continuum assumes that arbitrarily small distances are meaningful. Quantum mechanics suggests otherwise. Something must give. This realization motivated several independent research programs, each proposing that spacetime is not fundamentally continuous, but emerges from discrete or relational structures. These approaches do not agree on details. What they share is a rejection of smoothness as a starting point. Loop quantum gravity is one of the most direct responses to this problem. Developed in the late 20th century by researchers including Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, the theory begins by rewriting general relativity in a form more compatible with quantization. Instead of treating geometry as a smooth field, it describes it in terms of networks. In this framework, space is composed of nodes connected by links, forming what are called spin networks. These networks are not embedded in spacetime, they are spacetime. Areas and volumes take on discrete values, much like energy levels in an atom. There is a smallest possible area and a smallest possible volume. Below these, geometry cannot be subdivided. This discreteness is not imposed arbitrarily. It arises from the mathematical structure of the theory once gravity is quantized consistently. At large scales, where many such units combine, smooth geometry re-emerges as an effective description. At small scales, continuity disappears. Causal dynamical triangulations approach the problem from a different angle. Instead of quantizing geometry directly, this framework builds spacetime from simple building blocks assembled according to strict rules. These blocks are higher-dimensional analogues of triangles and tetrahedra, glued together in ways that preserve causal order. The key idea is that spacetime geometry emerges statistically from the collective behavior of these blocks. When assembled randomly without constraints, the result is pathological. But when causal structure is enforced, a well-behaved spacetime emerges at large scales. Numerical simulations conducted over decades have shown that four-dimensional spacetime can arise naturally from this process. At small scales, geometry appears highly irregular. At large scales, it smooths out. Continuity is not fundamental. It is emergent. Holographic ideas take yet another route. Inspired by black hole thermodynamics and developed through work by Gerard Hooft and Leonard Susskind, the holographic principle suggests that the information content of a region of spacetime is proportional not to its volume, but to its boundary area. This insight gained mathematical precision through the ADS-CFT correspondence developed in the late 1990s. In this framework, a gravitational theory in a higher dimensional spacetime is equivalent to a quantum field theory without gravity on its lower dimensional boundary. Geometry in the bulk emerges from quantum information on the boundary. Here, spacetime is not built from geometric pieces at all. It is built from entanglement patterns. Distance corresponds to correlations. Geometry reflects information structure. Smooth spacetime appears when entanglement has the right form. Each of these frameworks replaces continuity with something else. Networks, simplices, information, non-claim experimental confirmation. All are constrained by observation. What unites them is necessity. Smooth spacetime cannot survive indefinitely. It must give way to a deeper description that remains consistent under quantum conditions. Observations reinforce this conclusion indirectly. NASA and ESA missions have mapped the universe with extraordinary precision. Gravitational waves propagate coherently across millions of light-years. Light from distant quasars remains sharply defined after traveling for billions of years. These facts tell us that any underlying discreteness must average out efficiently at large scales. Discrete does not mean jagged. It does not mean noisy. Atoms do not make solids rough at human scales. They make them stable. In the same way, discrete spacetime could underlie smooth geometry without disrupting observable physics. Historical parallels are instructive. In the 19th century, matter was assumed continuous. The discovery of atoms replaced that assumption. Fluids remained smooth at everyday scales. Thermodynamics remained valid. But the deeper description changed fundamentally. Spacetime may be undergoing a similar transition. Carl Sagan once remarked, "We are made of star stuff." In a more technical sense, spacetime itself may be made of something else, something that does not resemble space or time in the classical sense. That statement is not poetic. It is a recognition that fundamental descriptions often look nothing like the phenomena they explain. None of the current frameworks provide a final answer. They compete, they constrain one another. They are judged not by elegance alone, but by their ability to reproduce known physics while remaining internally consistent. What matters is that smooth geometry is no longer assumed, it is derived. It appears when deeper structures align correctly. This shift changes how questions are framed. Instead of asking why spacetime fluctuates, physicists ask what spacetime is made of. Instead of treating geometry as fundamental, they treat it as emergent. As observations continue to tighten constraints, some frameworks will fail, others will survive. The process will be quiet, as it was with quasars and quantum foam. At this point, the implications extend beyond geometry itself. If spacetime arises from something deeper, then the basic features of reality follow from those hidden structures, defining which forms of matter, interaction, and stability are even possible. Part 10. Why does the nature of spacetime decide what reality can be? Everything we have discussed so far converges on one unsettling fact. Reality is not defined first by objects, particles, or even forces. It is defined by the structure of spacetime itself. Before matter can exist, before energy can propagate, before cause can lead to effect, spacetime sets the rules. If those rules change, everything built upon them must change as well. This conclusion is not philosophical. It emerges from data. We began this series with photons, and we return to them now because they have never stopped traveling. Light emitted from the first stars, from young galaxies observed by the James Webb Space Telescope, from quasars whose radiation began its journey more than 10 billion years ago, continues to arrive with remarkable fidelity. These photons carry more than images of distant objects. They carry information about the medium they crossed. They are records of what spacetime allowed. Photons reveal something fundamental. They respond directly to geometry. They do not possess mass that could shield them from spacetime's structure. They do not have an internal clock that could drift independently. Their behavior is defined entirely by spacetime itself. Because of this, light becomes a boundary marker. It tells us what kinds of structures spacetime permits and which ones it forbids. Throughout this exploration, simple ideas have repeatedly failed. The idea that empty space is inert failed. The idea that spacetime remains smooth at all scales failed. The idea that quantum fluctuations and geometric fluctuations are the same failed. The idea that microscopic structure would obviously disrupt macroscopic physics failed. Each failure was not dramatic. Each was quiet, enforced by observation. Nature did not argue. It measured. Data from NASA, ESA, and ground-based observatories have shown us where freedom ends. Photons arrive on time. Spectra remain sharp. Interference persists. Gravitational waves propagate at the same speed as light. Atomic clocks remain synchronized. These facts place boundaries around speculation. They tell us that spacetime, whatever its deepest nature, preserves coherence with extraordinary precision. This preservation has consequences. It means that spacetime is not merely a backdrop. It is an active filter. Only certain forms of reality can exist within it. Only certain interactions remain stable. Only certain structures persist long enough to be observed. If spacetime were more irregular, atoms could not form reliably. Spectral lines would smear. Chemistry would fail. If causality were weaker, signals would blur, and structure could not accumulate. If the speed of light varied, navigation across cosmic distances would collapse. The universe we observe would not exist. This is why the nature of spacetime decides what reality can be. Quantum gravity frameworks approach this from different angles, but they converge on the same implication. Geometry may not be fundamental, yet it governs everything built upon it. Whether spacetime emerges from networks, from simplices, or from quantum information, its effective behavior determines what particles do, how fields propagate, and which correlations survive. Photons sit at the center of this determination. They move at the maximum allowed speed. They define causal limits. They integrate spacetime's structure along their entire path. Every photon detected is a test passed. Every absence of distortion is a constraint enforced. This is why the lack of dramatic quantum gravity signatures is not disappointing. It is revealing. It tells us that spacetime's deepest structure must be subtle, disciplined, and compatible with coherence. The frontier is not a place where known physics breaks loudly. It is a place where it survives under extreme pressure. Historical parallels help clarify the significance. When atoms were proposed, they were not directly observed. Their existence was inferred from patterns in spectra, from heat capacities, from chemical ratios. Matter appeared continuous at everyday scales, yet its behavior demanded discreteness beneath. The same pattern now appears with spacetime. Spacetime behaves smoothly at observable scales. Yet when theories are pushed consistently, smoothness cannot remain fundamental. Something beneath it must enforce the behavior we see. Carl Sagan once wrote, "We live in a universe governed by chance and necessity. In this context, necessity dominates. The structure of spacetime constrains what chance can produce. It decides which fluctuations fade and which accumulate. It decides whether complexity survives or dissolves. Photons continue to cross the universe, largely unaltered. That fact alone rules out countless possibilities. It tells us that spacetime cannot be arbitrarily noisy. It cannot be arbitrarily granular. It cannot violate symmetry, where symmetry is observed. It must allow deep structure without revealing it easily. The frontier remains open not because we lack ideas, but because nature enforces restraint. Theories must earn survival through consistency with everything we already see. Each new observation tightens the boundary further. James Webb Space Telescope observations now push that boundary deeper into the early universe. Light from the first galaxies shows that spacetime maintained coherence under conditions far more extreme than those present today. This continuity across cosmic history reinforces the same lesson. Whatever spacetime is made of, it has been enforcing its rules since the beginning. The final picture is not one of completion. It is one of clarity. We know where simple models fail. We know where observations speak decisively. We know where uncertainty remains. Spacetime may not be fundamental, but it is decisive. It governs what can exist, what can connect, and what can persist long enough to be known. Photons will keep traveling. They will continue to arrive quietly, carrying information about distant sources and about spacetime itself. They wait for better instruments, better theories, better questions. The universe does not hide its structure maliciously. It hides it behind consistency. As this series comes to rest, there is no final answer to deliver. There is only a refined boundary between what is ruled out and what remains possible. That boundary is where future discovery will occur. For now, the universe continues to behave exactly as observed. Light continues to move at its invariant speed. Geometry continues to enforce coherence. Reality continues to exist within the constraints spacetime allows. If you're listening near the end of a long day, or in the hours when rest is beginning to feel close, this feels like a natural place to pause. Photons will continue their paths whether we follow them or not, and the universe will continue to hold together, just as it has across immense spans of time. I hope that steadiness stays with you for a while, the sense that even across billions of years and unimaginable distances, things remain connected, reliable, and intact. May your thoughts slow down with that rhythm, and may sleep come comfortably tonight. Good night, and thank you for spending this time here.